All right, so let's quickly recap what we did last time. So we started with higher order equations, and we showed that we can extend the idea of Wronskian to understand if the solutions that you write down are linearly independent or not. And we also found that if you have an nth order equation, you have n linearly independent solutions, and the general solution can always be written as a linear sum of these linearly independent solutions, as I've done here, right? And then we started doing a couple of constant coefficient problems, and then we discussed that the method that we will employ is exactly the same as what we did for the second order case. We will substitute y as some e to the lambda x, and then write down a characteristic equation, which will turn in your differential equation into a polynomial equation in the roots lambda. And then we will figure out lambda, and depending on what lambda is, you can have solutions as e to the lambda x or minus lambda x, or oscillatory solutions, right? And now, up till now, we have discussed the case of distinct real roots, and then in the case of distinct real roots, we actually showed explicitly the construction the Wronskian is actually non-zero because it's a product of different differences of lambdas. So now we have to understand what happens if there is multiple real roots. So in the recall, in the second order case, so let us start with the case of multiple, multiple real roots. Okay, so recall the second order case. So what did we have there? Suppose if you had a second order equation, for example, y double plus a1 y prime plus a0 y equals 0 has two solutions. Let us say that roots of the characteristic equation are lambda and lambda, okay, a double real root. Then what did we say? Suppose if we had to write down the general particular solution, we wrote this as a linear combination of these two in a slightly different fashion. So suppose if we are indeed solving the inhomogeneous equation with some r of x, roots of the characteristic equation having double real roots implies that suppose if this is r of x equals e of x, e to the x, say, right? Then what did we do? The particular solution was c1 e to the lambda. So the homogeneous solution is the solution to the characteristic equation, and yp cannot have any solution already contained in YH, right? So this was our deciding criterion. So if you had a solution in YP that was already in YH, you basically discarded this piece of the particular solution YP, right? So then the way you went about determining this is, of course, we discussed two methods, the variation of parameters and method of undetermined coefficients. And then in both these methods, we discussed, in the case of second order, how to get the solution in the general case. So today's lecture, we will try to extend these results to the nth order case. Okay, so I will not give you a lot of proofs or theorems, but I will work out a couple of examples in which I will show explicitly how to extend these two techniques that you already know for second order, and that will also work for higher order. Okay. So before we get there, let us first discuss the case of multiple roots, multiple real roots, and how do you attack this particular problem in this case. Okay. So remember that in the second order case, you basically, if you had a double root, you wrote down the solution as C1 plus C2, C1 plus C2x times e to the lambda x, right? So if you recall, so you basically multiplied the second solution was basically the first solution times an x. Okay, so please keep this in mind. we will extend this to the third order case and the fourth order case and any order case. So before we do that, let us just work out a small example that is taken from your textbook. This is actually a simple equation that I can actually solve very easily to get multiple roots. So 3, again, my notation is that yn is dny over dx to the n. Okay. All right. So let us work out the, so let us substitute y is e to the lambda x, and this gives me the characteristic equation. Remember that the power of lambda that is coming out is exactly the number of times you differentiate this expression, right? So please do mute if you are not speaking. All right. So this gives me the characteristic equation as lambda to the 5 minus 3 lambda to the 4th plus 3 lambda cubed minus lambda squared equals 0. I don't want e to the lambda x to be 0. So the stuff that multiplies e to the lambda x has to be equal to 0. Okay. So what does this imply? So I can pull out a lambda square from this, and this becomes lambda cubed. And the stuff inside the brackets, as you can clearly see, is basically lambda minus 1 the whole cubed. Okay, so the roots of this equation are 0 and 1, and 0 appears twice and 1 appears 3 times. So the roots are 0, 0, 1, 1, and 1. Okay, now I know how to attack the double root case. The 0 appears twice, so I know how to deal with that. But how to deal with the root 1 that appears 3 times? Well, I will write down the solution and then we will justify it. You will actually see that it's not very hard to accept this. The solution is given by, well, if lambda is 0, then the same second order double root situation applies, right? So we wrote it as c1 plus c2x times e to the lambda x, but lambda is 0, so e to the 0 is just 1. So the two linearly independent solutions corresponding to lambda is equal to 0 root are basically c1 plus c2x. Okay. Now 1 appears 3 times. Well, if 1 appears only 2 times, I can write down the solution as c3 plus c4x times e to the x, corresponding to lambda equal to 1. But what do I do for the third root? Well, just like if I had a double root, I multiplied the solution by x to get a second linearly independent solution. If I have a third root, then I will simply multiply it by x squared, and that will give me a third linearly independent solution. So the corresponding to lambda equal to 1, I can write down the solution as c3 plus c4x plus c5x squared e to the x. Okay. So just like in the case of a double root, you multiplied e to the x by x. In the case of a triple root, you multiply e to the x by x squared. If 1 appeared, for example, 4 times, I will have another linearly independent solution, which is x cubed e to the x, and so on and so forth. So for each time this root appears, you multiply it by corresponding power of x. Okay. So this is the most general solution. So you can actually guess that just like x and e to the x are linearly independent solutions, this set 1, x squared, x cubed, blah, blah, blah. This polynomial, this is also a linearly independent set of functions. Okay, so you can actually work out the Wronskian for this and satisfy yourself that for any finite number of terms, that this is indeed non-zero. Okay, so you can actually clearly verify that these 5 are linearly independent solutions. I'll leave that to you. But what I want to do now is to actually show you that this actually makes sense. And this we can show by using a cute trick. So let us start with the differential equation itself. What is the differential equation? The differential equation is yn plus an minus 1, yn minus 1, all the way to a1 y prime plus a0 y equals 0. Okay. And as I told you, you can factor out all the operators hitting y, right? So I can write this as dn dx to the n plus an minus 1 dn minus 1 dxn minus 1 plus a1 ddx plus a0, this weird looking object hitting y equals 0. And I can pretend that whatever inside the bracket, this defines the notion of an operator. So I'll call this as L operator hitting y equals 0. This is a compact way of writing this exact same equation. Okay. So now how do I solve this? I solve this by writing down the characteristic equation. So I substitute y is e to the lambda x and figure out what the characteristic equation is. How will the characteristic equation look like? Well, for each differentiation, I'm going to pull out one factor of lambda. So the characteristic equation in this case is going to be L hitting e to the lambda x, because that is my function, would be equal to dn dx to the n is going to pull down n factors of lambda plus a n minus 1 lambda n minus 1 plus all the way till a1 lambda plus a0 hitting e to the lambda x. Okay. And since I'm pretending that e to the lambda x is a solution, this has to be equal to 0. Okay. This defines what the characteristic equation is for me. Since e to the lambda x is not equal to 0, I don't want the solution itself to be 0. I say that this guy is 0 and solve for the roots. This is what you have always done. Okay. Now, what happens in the case when one of the roots appears like 2 times, 3 times, 5 times, 17 times, whatever it is? Okay, so let us understand this in a general setting. So let us say that this is an nth order, the way I have written, and let a particular root, let us say, let lambda equal to lambda 1, that particular root appear m times. Okay. Now m can be less than n or m equals n. For example, I can have a cubic equation with 3 degenerate roots, lambda minus 1 the whole cubed equal to 0, right? So there m equals n because the root that repeats itself appears as many times as it is allowed. But it can also appear less times. For example, in this example that we discussed, it's a 5th order equation and the root 0 appears twice and the root 1 appears 3 times. So let us take a look at this particular case where a root appears m times. Then how can I write this equation? I can write this equation L e to the lambda x as, since I can factor this characteristic equation, and since by assumption lambda 1 appears m times, this equation is basically lambda minus lambda 1 to the power m, right? And then I will assume that the other roots are either degenerate or non-degenerate. I don't care. I'm only looking at lambda 1 in particular. So let us say lambda minus lambda n plus 1 all the way to lambda minus lambda n e to the lambda x. Okay. Now this guy is some polynomial in lambda. I don't care exactly what the form of this polynomial. So I'll just call this polynomial h of lambda. Okay. So assuming that the root lambda 1 appears m times, I'm going to write this equation as lambda minus lambda 1 to the power m times some h of lambda times e to the lambda x. Okay, so this is my differential equation. Any questions or comments about this? Is this okay? So what is my goal here? My goal here is to show you that, look, e to the lambda x is clearly a solution for some root lambda equal to lambda 1 or lambda equal to lambda 2, whatever it is. But if the root lambda 1 is degenerate and appears multiple times, then my goal here is to show you, is to convince you that x times e to the lambda x is also a solution. What do I mean by a solution? Again, if lambda is a solution, then L times e to the lambda x equal to 0. This implies that e to the lambda x is a solution. Right? If x times e to the lambda x is also a solution, as we have discussed previously, then this equation should hold. If x squared times e to the lambda x is also a solution, L times x squared e to the lambda x also should be 0. So my goal is to show that in the case of degenerate roots, these equations make sense. Okay. In the case of non-degenerate roots, we don't need this procedure. But if you have roots that repeat, then these equations make sense. If e to the lambda x is a solution for lambda equal to lambda 1, then x times e to the lambda 1x is also a solution. This we will show by a cute trick. Pretend that this lambda is some kind of a variable and differentiate both sides. I think we also employed this trick somewhere before, but I forget exactly where. So differentiate this expression both sides with respect to lambda, okay, assuming that lambda is a variable. Remember, I'm not differentiating with respect to x, okay, so I'm differentiating this guy. So d lambda L e to the lambda x equals d lambda minus lambda 1 to the m h of lambda e to the lambda x. Okay. Now let us look at the right hand side. That is rather straightforward. Sorry. Right hand side of this equation. I can write this as I'll first differentiate this guy, keeping the rest constant, so on and so forth. So this becomes m minus 1 e to the lambda x plus lambda minus lambda 1 times d lambda of the rest of the stuff. It makes no sense to expand this further because I don't know what h of lambda is in general. Right? So I'm just keeping everything fairly general. So I'll just write it as this and leave it at this point. But what's interesting is what happens to the left-hand side. Remember that this operator L has differentiations again, but these differentiations are with respect to x. It has nothing to do with lambda. In other words, differentiations with respect to lambda and differentiations with respect to x commute. I can interchange the order. So I can write d lambda L e to the lambda x. So d lambda is going to pull down factors of x, and this has nothing to do with ddx. So I might as well write this. In fact, you can take a very small expression like d cubed, dx cubed, whatever it is, and satisfy yourself that this is true. Okay, don't take my word for granted. I can write this as L d lambda e to the lambda x. Okay. If I differentiate e to the lambda x with respect to lambda, that's going to pull down a factor of x. So this is basically L x e to the lambda x. Okay. So now let me write this equation again. L hitting not e to the lambda x this time, but x times e to the lambda x would be equal to m h of lambda e to the lambda x plus lambda minus lambda 1 d lambda e to the lambda x. Okay. Now, if lambda equals lambda 1 is a root, then let us put in lambda equals lambda 1 on both sides. You actually find L x e to the lambda 1x is actually 0. Because whatever this guy is, it is multiplied by 0 on the outside. Okay. Which proves to you that if lambda 1 is a repeating root, e to the lambda 1x is a solution, and x times e to the lambda 1x is also a solution. How do I show the x squared e to the lambda x is also a solution? That is also trivial. Instead of differentiating once with respect to lambda, differentiate twice. Okay, if you differentiate twice with respect to lambda, then d square d lambda square of L e to the lambda x, okay, would pull down two factors of x. So this will become L x square e to the lambda x. And do the exact same thing on the right hand side and show that every term on the right hand side has a factor of lambda minus lambda 1. So if you put lambda equals lambda 1, the right hand side vanishes. So x squared e to the lambda x is also a solution if lambda is a repeating root. Okay. So in the case of repeating roots in higher order equations, the way you construct the solution is a simple extension of the second order case. So if lambda 1 is a repeating root, then the solution, linearly independent solutions corresponding to lambda 1 are e to the lambda 1x, x times e to the lambda 1x, x squared times e to the lambda 1x, x cubed times e to the lambda 1x, and so on and so forth. How many ever times lambda 1 appears. Okay. So this is the general procedure in the case of higher order equations with repeating roots. So what happens if there is multiple complex roots instead of multiple real roots? Multiple complex roots. Okay, so let us say that you have two roots, lambda is gamma plus I omega. Okay, and let us say that this appears 2 times. Okay, so remember that if lambda is a solution, lambda bar is also a solution. So this is also a solution, right? And if lambda appears twice, lambda bar also appears twice because they have to always occur in pairs. So in this case, your linearly independent solutions would be, I can trade the e to the I omega x for cosine and sine. And in this case, I can write my solutions to be e to the gamma x cosine omega x, x e to the gamma x cosine omega x, e to the gamma x sine omega x, and x e to the gamma x sine omega x. If I have lambda appearing 3 times, lambda bar also appears 3 times, then I will have an x squared e to the lambda x cosine omega x and an x squared e to the gamma x sine omega x. 2 other roots to give me 6 independent solutions, and so on and so forth. Okay. These instances are rather rare, but you should be aware of them and how to solve such problems. Okay. So multiple complex roots are a simple extension of multiple real roots. Simply trade your complex roots for the real parameters cosine and sine, and then you simply write down a linear combination of them. If the roots are repeating, then of course, just like in the case of real roots, you multiply them by x and x square and so on and so forth to construct the linearly independent solutions. Okay. Are there any questions or any comments about this? Because I'm now going to slightly shift gears and talk about how to extend the 2 techniques that you studied in the last couple of lectures. Questions or comments? Is this okay? All right. So let us now shift gears and talk a little bit about non-homogeneous. And I'm going to be very brief here. Higher order ODEs. Because the methods for solving them can be very simply understood by what you guys already know for second order stuff. Okay. So again, the general equation is yn plus pn minus 1, yn minus 1 plus p1 of x y prime plus p0 of x y equals some r of x. Okay. But we are going to talk about constant coefficients first. So if I have constant coefficients, then I will have an equation like yn plus an minus 1, yn minus 1 plus a1 y prime plus a0 y equals r of x. Okay. Now I can turn this into an initial value problem. If I want to turn this into an initial value problem, I should give you an initial condition. So I will say that y0 of x0 is some a1, sorry, y prime of x0 is a2, blah, 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 yn at x0 is some an. And with these initial conditions specified, you can go ahead and solve this initial value problem. Okay. Now there is 2 methods that we discussed to solve second order equations with constant coefficients. One was the method of undetermined coefficients, and the second was the method of variation of parameters. Okay, so I'm going to try and briefly tell you how these 2 things extend in higher order cases also. So method of undetermined coefficients. Again, I'm going to motivate this using an example, but let us quickly recap the second order case. So second order case was y double prime plus a1 y prime plus a0 y equals some r of x, right? And method of undetermined coefficients applies to simple cases of r of x like sines and cosines and exponentials and simple polynomials. And you know what the particular solutions are. You can simply guess what the particular solutions are, right? So if this is some e to the lambda x, and if none of this has lambda as a root for the homogeneous case, then your particular solution can be simply some c times e to the lambda x. If one of these guys has lambda as a, if one of the roots of this homogeneous equation has lambda as a root, then you should try yp as cx e to the lambda x, right? And if both the roots correspond to lambda, you should try yp as cx square e to the lambda x, right? And then the way you determine c is to demand that this solves this differential equation, plug this ansatz into the differential equation, and then figure out the value of c. Okay, this is the value of c is not gotten by initial value conditions. It is only gotten by the demand that your ansatz solves the differential equation. And then once you solve this, you write the general solution as the homogeneous solution plus the particular solution that you figured out. Okay, so we're going to extend the exact same thing to higher order stuff. So how are we going to do that? So I'll leave this in here because so let's take a third order equation just to be consistent. I'll call this y3 plus 3y2 plus 3y prime plus y is some e to the x or e to the minus x or whatever it is. So e to the x, let us say. Okay. Now I can also turn this into an initial value problem. I should give you three conditions. So let us say I give you y of 0 is a, y prime of 0 is b, and y double prime of 0 is c. My intention is not to solve the initial value problem, which I trust you know how to do by now, but to show how to approach this problem using undetermined coefficients. Okay, so how will you solve this problem? You will first solve this problem by writing down what the homogeneous equation is. So let us say y is some e to the lambda x, and the homogeneous equation gives me a characteristic equation. The characteristic equation for this guy, without belaboring the point, is plus 3 lambda plus 1 equals 0. Okay. And with this, you recognize as basically lambda plus 1 the whole cubed equal to 0. So you have a third order differential equation, which gives you a cubic characteristic equation. And it so happens in this case that the cubic equation has three degenerate roots. The roots are -1, -1, -1, nothing else. Right? So apply our rule. If you have degenerate roots, the solution is the first degenerate root you write as such as e to the lambda times x. The second one would be x times e to the lambda x. So the third one would be x squared times e to the lambda x. So the homogeneous solution is YH is excuse me, C1 lambda is -1, so minus x, plus C2x e to the minus x, plus C3x squared e to the minus x. Or you can write this as C1 plus C2x plus C3x squared times e to the minus x. Okay. All right. So the homogeneous solution is easy to guess, assuming that you know how to solve this cubic equation, which in this case is rather simple. The question is, how do you find the particular solution? So this is actually a case where R of x is indeed simple. It only has e to the x on the right hand side. But I cannot choose my particular solution as c times e to the minus x because it is already contained in this homogeneous equation, right? I cannot choose my particular solution as cx e to the minus x because that is also already contained in this homogeneous equation. I cannot choose my particular solution as cx squared e to the minus x because unfortunately that is also contained in the homogeneous equation. So the lowest non-trivial yp that I can consider in this particular case is yp is cx cubed e to the minus x. So this is the general methodology for undetermined coefficients. In case I had an equation where -1 only appears 2 times and the solutions was c1 plus c2x times e to the minus x plus c3 e to the 2x or something like that, then x squared e to the minus x might be a reasonable guess. But in this case, since the root appears thrice, both e to the, sorry, all three options, e to the minus x, x e to the minus x, and x square e to the minus x are out. Okay, so remember that this is true for this particular problem because this root appears 3 times. Oops, excuse me. Okay, so the rest is actually straightforward. By the way, you can actually show why you cannot consider these 3 solutions. If you are really adamant about choosing this, I will see if you say that no, you can still choose c e to the minus x, go ahead and choose it and see what happens. So let us actually choose it. The differential equation is y3 plus 3y2 plus 3y1 y prime plus y equals 0, right? So since I'm choosing, suppose I choose yp as c to the minus x, then yp prime is minus c, yp double prime is plus c, and yp triple prime is minus c. Substitute all of these guys in the parent equation. What do you get? You will actually find that you will be unable to determine c. Okay, so you will have minus c e to the minus x plus 3c e to the minus x minus 3c e to the minus x plus c e to the minus x equal to 0. And this only tells you that 0 equals 0 and there is no way to determine c. Okay, so that is the trouble you will run into if you choose a wrong consorts for this equation because of multiple roots. So the same thing will happen if you choose cx e to the minus x or x squared e to the minus x. I leave that to you to show yourself. So then how do we determine yp? So yp in this case is of course cx cubed e to the minus x. Okay, so demand that this is a solution. Demand yp solves, I'll call this a, and determine c. Okay, and in this case c will turn out to be, I think, 5. So then I can write the general solution to this equation as y equals yh plus yp. Yh we have figured out to be this guy, c1 plus c2x plus c3x squared e to the minus x plus 5x cubed e to the minus x. So go ahead and show that these 4 solutions are indeed linearly independent by writing on the Wronskian for it. Now, how do I figure out C1, C2, C3? Fix C1, C2, C3 using the initial conditions given. Okay. This is the general procedure. This is exactly what you did for the second order case also. So substitute y at 0, y prime at 0, and y double prime at 0. This gives you 3 equations, and you can solve for the 3 unknowns, C1, C2, and C3. And write down the particular solution for this particular initial value problem. Okay, so this is how you use undetermined coefficients in the case of higher order equations. The first possible trouble in this case is that you have to solve not a quadratic equation but a higher order equation. So you have to learn how to do some, at least you should learn how to solve cubic equations and how to factor things and so on and so forth. So once you get over that initial hump, the second thing that you have to worry about is how to write down your particular solution. In the case of simple r of x, like e to the x or sine x, don't write a particular solution that is already contained in the homogeneous solution. Write something that is not there, linearly independent of it. Then fix the constant in the particular solution by demanding that this solves the differential equation. Write the general solution and fix the constants in the general solution if so required, by appealing to the initial conditions. Okay, so this is how the method of undetermined coefficients extends to the higher order case. Any questions or any comments about this? Apart from the first part of solving a higher order equation, the rest is actually a carbon copy of what you already know. Except that the so-called rules that we discussed have to be modified, because you could have multiple roots and not just double roots. So if you have multiple roots, you should pay attention and not choose your YP as something that is already there in the homogeneous stuff. So that is another tricky thing that you have to sort of learn to navigate. Questions, comments? Okay. So as a slightly non-trivial extension of what we learned, let us also discuss the method of variation of parameters. Again, let us quickly recall what happens for the second order case. Recall the second order case, I had an equation which I cast into this form, y double prime plus a1y prime plus a0y equals some r of x. And I wrote down the particular solution in this case as minus y1, y2 r of x divided by the Wronskian w plus y2, y1 r of x Wronskian w, where y1 and y2 are the solutions to the homogeneous equation, linearly independent solutions to the homogeneous equation. I'll first write down what the answer is for extend this to higher order. Okay. The particular solution with a higher order equation is, so you have an equation like yn plus an minus 1, yn minus 1, a1y prime plus a0y equals r of x. The solution, the particular solution for this guy is yp. I'll write it in a cryptic form, but then we will unpack this and see that it is not very mysterious after all. K equals 1 to n yk integral wk divided by w Wronskian times r of x dx. Okay. So what are the common things in these two equations? So let us call this equation 1 and let us call this equation 2. Equation 1 is a sum of two terms. Equation 2 is a sum of n terms. Okay, this is understandable because we are dealing with an nth order equation. So equation 1 has some minus signs and plus signs, and there is no minus signs here. Okay, so that is something we have to understand what's going on here. And equation 1 has y2 times r and y1 times r inside the integral. And equation 2 has some kind of a function called wk. So what is this wk? So remember that yk k equals 1 to n are the linearly independent solutions of the homogeneous equation. Just like in equation 1, y1 and y2 are the solutions of the homogeneous equation. In this case, the homogeneous equation is a1y prime plus a0y equals 0. Okay. And the solutions of this guy are what I'm calling as y1, y2, y3 up to yn. So these are the yks appearing here, solutions of the homogeneous equation. So there is a solution outside and a solution inside. Here there is a solution outside, but what is this wk inside? Well, wk is a reduced Wronskian. It's not really reduced, but what you do is the following. Let us say that you are looking at the kth solution. Okay, so you can write down the Wronskian for the entire thing, right? So what's the Wronskian for the entire thing? So that is y1, y2, y3, yn, y1 prime, y1 double prime, y1 to the n. Similarly, fill out all these entries, and this will be your Wronskian. Okay. Assuming that y1, y2, etc. are linearly independent, this Wronskian will never be equal to 0. So which is why I can divide by it with impunity. Okay. Now, what is wk? So let us say k equal to 3. W3 in this is basically, you look at the third column, right? The third column here is y3 prime, y3 double prime, and so on, y3 to the n. And simply close your eyes and replace the third column with zeros everywhere and 1 in the last entry. So W3 would be, you leave the rest as it is, y1 prime, y1 to the n, y2, y2 prime, y2 to the n. And then when you come to 3, you simply put 0, 0, 0 all the way, and the last one should be 1. Don't put 0, 0 everywhere, that will become bad. And then the rest is as it is. This is the Wronskian corresponding to k equal to 3. Suppose if I'm looking at k equal to 7, then simply replace a 7th column with zeros everywhere and 1 in the last entry. Okay. So on and so forth. That will be your Wronskian. So the question is, where did this WK come from? Because we had a slightly simpler solution here. Okay, so I will show you that this WK is exactly what you had in the initial case also, even though we didn't discuss it that way. So if I want to apply it to n equal to 2, n equal to 2 case, I can write down the entire Wronskian, which is y1, y2, y1 prime, y2 prime. Okay. Now I can write down W1. What is W1? W1 would be, I replace the first column by 0 everywhere and 1 in the last entry. In this case, there is only 2. So I will write this as 0, 1, y2, y2 prime. What is this? This is equal to -2. W2 can be written as, I write the first column as it is and replace the second column with 0 and 1. And this is basically y1. Okay. So if I specialize this formula for n equal to 2, then what I get is yp equals k equals 1 to n yk integral wk over w r of x dx, right? So this is y1. I put first y equal to 1, w1 over w plus y2 w2 over w. Okay. But what is w1? We just figured out that w1 is just minus y2. So I can write this as minus y1 y2r over w plus y2 y1r over w. Okay, which is exactly what we had before. So there is nothing mysterious about this formula. The n equal to 2 of this formula gives you exactly what you had before. This is the general formula for variation of parameters. Okay. So I've given you what the solution is without actually proving it to you, but I've shown you that it makes sense in the limiting case where n equals 2. Okay. So then how do you practically apply this? The way you practically apply this is as follows. So let us say that you have an equation of this form. X cubed y3 minus 3x squared y2 plus 6x y prime minus 6y is x to the 4 log x. Okay, remember that variation of parameters can also be used in cases where you have non-varying coefficients, even though we did not do it that way. This is actually a special equation that I've written here. It's called the, if I forget the right hand side, this is a Euler-Cauchy equation. And even though it looks like the coefficients here are x dependent, I can do a change in variables and I can massage this into a constant coefficient problem. Okay, so we will discuss this later when we do series solutions, but this can be done. So then the way you solve this, again, this is an indication of what's going to come next. The way you solve the homogeneous equation in this case, the homogeneous equation is x. So again, if I have to be consistent, I have to bring it into a standard form. The standard form is the highest derivative shouldn't have anything out front. So I should divide this equation by x cubed. So if I divide this equation by x cubed, I can write this as y3 minus 3 over x, second derivative, plus 6 over x squared, first derivative, minus 6 over x cubed times y is x log x. So the homogeneous equation is y3 minus 3 over x y2 plus 6 over x square y prime minus 6 over x cubed y equals 0. So obviously I cannot simply write a solution like e to the lambda x because it won't solve it because of all the x's floating around. E to the lambda x only works for constant coefficients. I will show you starting tomorrow or next lecture that you can write down what is called a series solution, but this is a special case of series solution, and I will try a solution of the form x to the m. Okay, I'll justify this in more detail in the coming lectures, but notice that I can solve this by this onsorts y as some simple power of x. Then substituting this onsorts in the parent equation, I get a polynomial in x. But this polynomial can be easily solved, as you can easily see. The first term gives me sorry, I'll write it over here. m minus 1, m minus 2, x to the m minus 3. The second term gives me 3 over x, m minus 1, x to the m minus 2. The third term gives me 6 over x squared, m x to the m minus 1. And the fourth term gives me 6 over x cubed, x to the m equal to 0. Now you see that the structure of this equation is such that I can write this entire thing as m minus 1, m minus 2, minus 3m, m minus 1, plus 6m minus 6. The whole thing times x to the m minus 3 equal to 0. And since I don't want x to the m minus 3 to be equal to 0, this equation fixes my m. Okay, and you can show for this particular example that m can be 1 or 2 or 3. These are the roots of this equation, cubic equation in m. Okay, so the solution of the homogeneous equation in this case is yh equals c1x plus c2x squared plus c3x cubed. Okay, x to the m is your solution. Again, I leave it to you to show that the Wronskian of these three is non-zero. Okay, how do you show this? The Wronskian of these three is basically x, first derivative of x, which is 1, second derivative of x, which is 0, x squared, first derivative, second derivative, x cubed, first derivative, second derivative. Okay, and this thing is 2x cubed, which is non-zero. Okay, so certainly these three are linearly independent solutions. Okay, so if I want to apply the variation of parameters to this problem, I need to figure out what are the different WKs. In this case, how many WKs are there? Well, there is 3 roots, so there's 3 solutions: x, x squared, and x cubed. So there has to be 3 W's: W1, W2, W3. W1 would be the same Wronskian, but with the first column replaced by 0, 0, and 1. 0, 0, 1, x squared, 2x2, x cubed, 3x squared, 6x. Okay. W2 would be the second column replaced by 0, 0, 1. So this is x10, 0, 0, 1, x cubed, 3x squared, 6x. And W3 would be the third column replaced by 0, 0, 1, leaving the others intact. So x10, x squared, 2x2, 0, 0, 1. Okay. You can figure out all these 3 Wronskians, and then you can easily figure out the particular solution. In this case, r of x is, of course, the right hand side is x times logarithm x, right? So this is your equation. Where is this? This one. After putting it into the standard form by dividing by x cubed, r of x is x times logarithm x, and simply substitute everything in your particular solution. Yp is now k equals 1 to n yk integral wk over w r of x dx. Okay, so you know the yks, the solutions are basically x, x squared, and x cubed. You know the wks because you can figure out these 3 determinants. And you know r of x, which is x times logarithm x. So in this case, this is y1 w1 x log x by w plus y2 w2 x log x by w plus y3 w3 x log x by w. Okay. So the only issue here is to compute a bunch of determinants. Once you compute these bunches of determinants, you can simply plug everything in the general solution and figure out the particular solution in this case. Okay. Of course, this becomes progressively more complicated as you deal with higher order equations, obviously. So if you have a fourth order equation, you will have 4 roots and you'll have to contend with 4 by 4 determinants. It becomes a little more cumbersome, but in principle, it can be done. Okay. So this is how you extend the notion of variation of parameters to higher orders also. Okay. So I'll have to stop at this point. I wanted to talk to you about a very nice application of the bending of beams, but I think I'll push this to a tutorial and I'll explain how this problem is set up. So at this point, I will stop and please do ask if you have any questions or comments.